Now that we have our definition for pH, we start to define and describe the strength of acids and bases and how we calculate their pHs. First, we do have to differentiate between strong and weak. This definition will apply to both acids and bases. When we say that an acid is strong or that a base is strong, we are simply describing the degree of dissociation. When we say strong, we are assuming 100% dissociation. I'm actually going to put about 100%. It won't exactly be, if you were to go into lab and measure, a strong acid or strong base would not dissociate completely 100%, but they're very close. It's a very high degree of dissociation. And we're only describing the degree of dissociation. When we say that an acid or a base is strong, it tells us nothing about the concentration, its pH, or how reactive it can be. So, for example, HF is a very weak acid, but it is very reactive. According to Breaking Bad, I've never tried this, but apparently HF can dissolve a human body. I do know that HF is actually stored in plastic containers, because if it's stored in glass, it will actually start to etch through it. And so because of the hydrogen bonding in there, HF is a very reactive acid. It's weak. It doesn't dissociate completely, but it is very reactive. When we are describing weak acids or bases, these typically dissociate about 5%. So for purposes of lecture, we'll see that when we do calculations of percent dissociation, it's about 5. Again, these can range in the real world anywhere higher or lower than that. And again, weak acids and bases can be very reactive and dangerous. They just don't dissociate in water to a great degree. As a visual example for you, if I have an acid HX at 1 molar concentration, when this dissociates in water, notice that we've just now put it in water, dissociation means that it will break apart into ions. And so we have complete ions in here that are the same concentration as the original acid. So this is a strong acid, 100% dissociation. Versus our second picture here, putting HY in water. Notice that our initial acid concentration again is 1 molar, but only one of my molecules dissociated. And in fact, that's still too high a percentage dissociation for most weak acids. But notice that only one dissociated, the other 4 of my acid molecules stayed intact. So this is a weak acid with far less than 100% dissociation. So again, strong acids dissociate almost 100%. This means they don't set up equilibrium. It means when I put my strong acids in water, they're going to dissociate almost 100%, meaning that that reaction is going to go to completion. So for strong acids, we use a completion arrow in our reaction or in our equation. We'll discuss this in more detail coming up, but strong acids will have very weak conjugate bases. There are 7 strong acids, and you must know these. You have to memorize these, both by formula and by name. You should be able to write an equation for putting an acid in water and draw a solution for it. For our first example, we're going to work with hydrochloric acid. We actually already did this one, but just a reminder, hydrochloric acid in water, because HCl is a strong acid, and it helps to get in the habit of labeling these. Since that's strong, it's going to force my reaction to completion. I'm going to form the chloride ion and the hydronium ion. So in here, we're also going to draw solutions. We're going to draw what 10 molecules of hydrochloric acid will do in water. The number 10 is relatively random. It's enough for us to show degree of dissociation, but not so much to be overwhelming. So again, 10 molecules, a relatively random number. Any number works. I just chose 10 here. So again, if I start with 10 molecules of HCl, since this is going to completion and it dissociates in a 1-to-1 ratio, it means my HCl is going to completely dissociate, and all that's left in solution are my 10 hydronium ions and my 10 chloride ions. And so it's perfectly okay to use coefficients as your in your drawings. For a second example, we're going to work with sulfuric acid. And a reminder, when we're working with finding conjugate acids and conjugate bases, we're only transferring one proton at a time. So if I'm looking for the conjugate base of sulfuric acid, that's going to be hydrogen sulfate with a -1 charge. Sulfuric acid is still an acid, so I still get hydronium in here. So realize that, again, this is a strong acid. If I'm starting with 10 molecules of sulfuric acid, I'm going to produce 10 molecules of hydrogen sulfate and 10 molecules of hydronium in here. So I don't have any sulfuric acid left over because it's all completely dissociated. But what I do have in solution are completely dissociated ions, the product of this dissociation. All right, so on this slide, again, a reminder of our 7 strong acids, our equation for HCl, and the drawing that we already did. And a note here that for the dissociation of HCl, I will always show the equation in water because that's most accurate, where we get hydronium. However, realize I could just show the dissociation of HCl into H+ and chloride. Remember, previously I mentioned that if I have H+ in water, that H+ is technically going to attach to water and will end up forming hydronium ion. But for purposes of calculations, H3O+ is considered equivalent to H+. And so our question down here now is to calculate the pH of 0.25 molar HCl. I'm going to come back up and erase my markings on my equations because I want to use these to identify the amounts of substances. So if I'm starting with 0.25 molar HCl, realize that because this dissociates completely in a 1-to-1 ratio, the original concentration of HCl is my concentration of hydronium and chloride. Now, I don't care about the chloride concentration. Later on, that will become important. But for now, I just want to know my hydronium concentration. Key thing to notice, for all of our strong acids, even with the diatomic sulfuric acid, all of our strong acids will dissociate in a 1-to-1 ratio, meaning the original concentration of my acid, we can use HA to represent any monoprotic acid. The concentration of my acid will always equal the concentration of my hydronium. So when I go to calculate pH, that's going to be the equation negative log of concentration of hydronium. Well, I can use this information to figure out that this is going to be the negative log of 0.25. We expect a low pH. This is a strong acid. That's a decently high concentration. And recognize we have 2 sig figs in concentration, so we're going to go to 2 decimal places in pH. So this solution of HCl has a pH of 0.60. So here's a little bit more discussion of our relative strengths of conjugate acids and bases. So again, a strong acid ionizes completely in water. I put HCl in water, it will completely react to form hydronium and chloride. And that means that this reaction will not go in the reverse direction. Technically it does, but to simplify things for this class, we're going to assume it doesn't. And so because it doesn't go in the reverse direction, it means that this chloride ion has no affinity for a hydrogen ion, meaning that chloride is a very, very weak base. It doesn't want to grab a hydrogen ion to reform HCl. Even if it did, and this reaction went in the reverse direction, HCl would simply just dissociate again. And so this reaction does not go in the reverse. So the chloride ion, again, is a very weak conjugate base because HCl is such a strong acid. And so realize that there is an inverse relationship here. The stronger an acid, the weaker its conjugate base. Just an example to clarify that if chloride was going to act as a base in water, so let's say I just had chloride floating around from some salt. If chloride is in water, it's not going to react to form HCl because even if it did, again, this would redissociate to give us our original products. And so again, the stronger an acid, the weaker the conjugate base. All right, and now we go through the same steps and definitions of our strong bases. Again, strong means that it dissociates nearly 100%. We'll assume 100% so that our reactions go to completion and makes life easier, but it will be nearly 100%. The difference with strong bases is that these do not have conjugate acids, and that's because our strong bases are actually all Arrhenius bases. So remember, Arrhenius bases are defined as having hydroxide in them. Notice for our 8 strong bases, they all have hydroxide. And notice that the cation, the metal cation that's with each one, comes from groups 1 and 2. So it's all of group 1, and then it is strontium, calcium, and barium from group 2. So we should be able to write equations and draw solutions for our strong bases. Again, we're going to do the same 10 molecules of lithium hydroxide in water. The other difference with strong bases is that these don't react in water. Because they are soluble ionic compounds, they simply dissociate in water. If it makes you feel better, you're welcome to put water on the arrow to show that it is dissociating in water. And again, for drawing purposes, 10 is relatively random. Any number is sufficient here, but again, this one dissociates in a 1-to-1 ratio. So I don't have any lithium hydroxide left over, but I do have 10 lithium ions and 10 hydroxide ions. So make sure here, put a little space in between your 10 and your O for the oxygen so it doesn't all lump together. Let's also try calcium hydroxide. So remember that calcium comes from group 2. That means its formula is CaOH2. It is still strong, so it's going to completely dissociate. But now when it does that, it's going to dissociate into calcium 2+ ions and 2 hydroxide ions. So if I want to draw 10 molecules of calcium in here, or start with 10 molecules, I'm going to end up with 10 calcium ions, but 20 hydroxide ions because of the stoichiometry. Strongest and best recommendation I can make is to always write the equation for what a substance is doing in water, because the common mistake I see is students forgetting about the 2-to-1 ratio here. And so for this solution, we produce 10 calciums and 20 hydroxides. So again, here's our drawing for lithium that we already did. So now we want to calculate the pH of each of these solutions. So again, for lithium hydroxide, we're given an original concentration of 0.015 molar, which means both lithium and hydroxide are that exact same concentration. So realize I know hydroxide concentration, which means first I'm going to calculate my pOH. That is going to be the negative log of hydroxide concentration. We use the same rules of sig figs for POH that we do for pH. 2 sig figs here gives us 2 decimal places. But realize that POH is not my final answer, right? So I don't round early here. I'm going to keep extra digits in this one because I'm not done until I calculate my pH. Remember, easiest thing to do at this point is use the sum of pH and POH as 14. And so moving the POH to the other side, I can calculate pH. Now I can round for sig figs. So again, 2 sig figs means I'm going to have 2 decimal places in my final answer. And this number makes sense. This is a strong base, and so I expect a high pH value. And our last example, we want to calculate the pH for our calcium hydroxide. So for this one, as a shortcut, I'm going to write my dissociation equation to the right of this. And recognize that if calcium hydroxide is 0.36 molar, that the calcium ion is going to be 0.36 molar, but my hydroxide is going to be 2 times that value. And that will be a 0.72 molar. Now I go through the same steps I used up above for the lithium hydroxide. I'm going to take my POH first. Again, I'm going to keep extra digits here because it is not my final answer. And to get pH will be a 14 minus that value. So now we look at sig figs. 2 sig figs in concentration gives us 2 decimal places in pH. We end with a pH of 13.86. So for 2 reasons, it makes sense that this is much higher than lithium hydroxide. One is we have a higher initial concentration. So the higher the initial concentration, the more dramatic the pH would be for bases, much higher, for acids, much lower. But also I have 2 hydroxides here. I'm producing twice as much hydroxide here, which should generate an even higher pH value.